So we're now going to talk about the limit comparison test. Let's begin with formulating it. So you assume you have two positive series, so you have AK and BK, and let's assume that they are strictly positive, such that the limit of their quotient is equal to some L for L between 0 and infinity, but not including 0 and infinity. Then what happens is that the series AK, say k goes from 1 to infinity, converges if and only if the same holds for the series with terms bk. So if this limit here, the limit of their quotients, is equal to a finite non-zero number, then if one series converges, the other series converges. And similarly, if one series doesn't converge, so this guy diverges, then the same holds true for him. So this is a comparison test where you don't compare with an inequality, but you compare with a limit. And I'm not going to prove this here, but we're going to look at an example where we essentially do every step in the proof, and I leave it as an exercise for you to generalize this into a proof. So what example would we look at? Well, let's take basically anything. So does the sum square root k squared plus k plus 1 divided by k squared plus 1 converge or not? And here k can start from 0 or 1 or whatever. All is good. And just as in the usual comparison tests, the first thing we need to do is use our intuition to somehow figure out who we should compare these guys to. So we can think of these as our AKs, and then we need to figure out, okay, what is a suitable BK? And the beauty of this limit comparison test is that this intuitive step is basically the same as the actual computation here. So let's do the intuition. So we need to know how these terms look for large K. So for large K, we have the following. So that's square root of k squared plus k plus 1 divided by this is more or less the same as. And then we can see that this 1 doesn't matter and this 1 doesn't matter. And inside of here, this k doesn't matter. So this would be square root of k squared divided by k squared, which is k divided by k squared 1 over k. So intuitively, I'm thinking that these guys here ought to behave like the terms in the harmonic series. So everything should diverge here. But I mean, so when you do the usual comparison test, that means, okay, now we know which way to point our inequalities in order to get an inequality between this and this. But in the limit comparison test, we just do the following. We need to check this limit. So formal step. So we now do the lim, k goes to infinity, and then I do my AKs here, and then I do my BK down here, like this. So I have this quotient divided by this quotient, and then we tidy this up. So I'm moving this guy up. So I have k now, this thing here. This looks a little bit like a mess, but when we compute such limits, recall, so we need to figure out who's the strongest guy on top and who's the strongest guy below, and then factor out. So below it's k squared. So I'm doing k squared here, and I'm having 1 plus 1 over k squared. And above, well, that k, I'm putting outside, of course. And then here I'm taking that k squared outside. And when k squared moves outside of the square root, it becomes a k. So I've got another k here. What's left inside of here is a 1 for him, and then a 1 over k there. And this guy becomes a 1 over k. So if you're unsure of this, just multiply a single k back everywhere here. You see this becomes a 1. That single k becomes a k squared when it moves inside of the square root, putting a k squared here, and a k squared divided by k here, giving a k. And then we're basically done because these two guys kill each other. This goes to 0, this goes to 0, this goes to 0. So all that is left here is this. And I tend to write out everything like this when I evaluate the limit, because then you kind of clearly tell the reader how each term acts. And this is 1 over 1, which is 1. Now I said, so this is how you would apply the limit comparison test. So now we're done. Now we did the formal step correctly. And I guess if you want to write conclusion here, so by limit comparison test, our series diverges since the harmonic series diverges. But what if we didn't have the limit comparison test? So let's take away this, and let's say that, okay, so we made this computation here. So we know now that this limit here is equal to 1. How can we use the knowledge of this limit to make the conclusion that this behaves in the same way as the harmonic series? So let's take a quick look at this. So let's do a heuristic here. Heuristic means basically hand waving. So for large k, we know that these terms here divided by these terms are really, really close to 1. Now, can we make that more precise? Well, if we use the definition of the limit, so then we know that for every epsilon, there exists an n such that when k is bigger than n, we have that this thing here, minus 1, remember there's a parenthesis here, is smaller than epsilon. Now, if I have some value x smaller than some positive value r, then it's a result from the course that you can open up the inequality and do this thing here. So I can definitely open up here, having all of this thing here play the role as my x and this being my r. So I can open this up, then I could put my minus epsilon here. Now, then I can add by 1 on all sides. So I'm getting here 1 minus epsilon, and then just this thing here. And adding 1 kills this, and I'm getting this. So now I know that whatever epsilon I choose here, then by choosing k large enough, I'm having this inequality here. So this quotient here will be as close to 1 as I want by choosing k large. And then we can do a specific choice here. We can do epsilon equals to 0, 1. Why not? Then this becomes 0.9, and this becomes 1.1. So this is now 0.9, and this is 1.1. So you can say, so there exists an n such that k bigger than n implies this. So I have no idea how big, maybe a million, a trillion, or 10, who knows? But I know that if I take my k large enough, I get this. Now I can multiply up the 1 over k's. Just delete this. So I have 0.9 times 1 over k, and this 1.1 times 1 over k. I can take away this. So what does this mean? Well, this means that I can use my usual comparison. So this and this can be used in the usual comparison test. Meaning that if the series with these terms converges, then the series with these terms will converge. And if the series with these terms diverges, then the series with these terms will diverge. Now, of course, if I sum this 1 over k's, doesn't matter if I multiply by 0.9 or 0.5 or whatever, just as long as this is a positive number. Then if I sum up these terms, I will get something that diverges since the harmonic series diverges. Hence, this guy has to diverge. So we conclude by usual comparison test that our sum, our series here, diverges since diverges, like this. And of course, I should put my limits here from 1 to infinity. And then, of course, you can see here, oh, wait a second, I'm only doing this comparison for k bigger than n. So here, really, I should have n plus 1 and n plus 1. What does this mean? Well, of course, this means I've only just proven that this tail diverges. But of course, if a tail of an infinite series diverges, then so does the entire infinite series. And we're done. So this basically here is what you can generalize quite directly to a proof of the limit comparison test.